Watch the coast. A wall of gray water rolls in off the Pacific, and for 3 days it does not stop. Rivers jump their banks. Hillsides slide into the road. A month of rain falls in a single day. It looks like a storm. It is the far end of a river, not a river on the ground. A river in the sky, more than 1,000 kilometers long and only a few hundred wide, reaching from the warm tropics all the way to the coast, and you cannot see a drop of it. Pull back far enough though, and it appears. On a satellite that watches water vapor instead of light, there it is. A bright narrow ribbon of moisture, bent across the ocean like a fire hose aimed at the land, and a single one of these ribbons can carry more water than the mouth of the Amazon, through the air, over your head. A thing as wide as a country, holding as much water as the planet's greatest river, and from the ground it looks like nothing more than a low, gray, heavy sky. No one standing under it can see the river. They only feel the rain begin and watch it refuse to stop. We call them atmospheric rivers, and by the numbers they are the largest rivers on Earth. They are also a trap the West cannot escape. The very same ribbons deliver much of the water that fills the reservoirs and ends the droughts, and they deliver most of the worst floods. Same river. One arrives gently and saves the year. The next arrives a little stronger, in just the wrong place, and breaks it. The line between the two is thin, and it moves. So by the end of this you will see where these rivers come from, why a strip of sky that narrow can move an ocean's worth of water, and the one thing about them we still cannot reliably call in advance. Where the river will land. To understand a river in the sky, start with the sky's water. Every ocean, every lake, every wet leaf is quietly giving water up to the air. Sunlight pours energy into the surface, and the water answers by turning to vapor and rising invisible into the atmosphere. Here is the strange part. The air does not actually hold very much. If you wrung every last drop of water out of the entire atmosphere at once and let it fall, it would cover the whole planet in only about 2.5 centimeters of rain. That is the sky's complete supply at any given moment. A thin film. All the rain, all the snow, every storm you have ever stood in is drawn from a layer of moisture you could in principle rinse off the planet in an afternoon. But it never sits still. The water in the air is fully replaced about every 9 days. Evaporate, drift, gather, fall, and begin again. The atmosphere is not a tank, it is a conveyor. A thin, fast layer that picks water up over the warm oceans and sets it down somewhere far away. And the warmer the ocean it crosses, the more water it can take on before it leaves. And it does not move that water evenly. You might picture moisture spread in a smooth haze all around the globe. It is not. Most of the water actually on the move is bunched into a small handful of narrow lanes. The sky has weather nearly everywhere, but it has real plumbing in only a few places. And those lanes are the rivers we are chasing. For most of the history of weather forecasting, no one drew those lanes. Forecasters saw storms and fronts, not rivers. The instruments of the day mapped pressure and temperature, not where the water itself was streaming. The rivers were hiding in plain sight, buried inside the data, with no one adding it all up. Then in the early 1990s, 2 scientists, Yong Zhu and Reginald Newell, did the accounting on a global scale. They added up how much water vapor was moving from the tropics toward the poles, and exactly where it was going. What they found rearranged the whole picture. At any given moment, almost all of that poleward water, more than 90% of it, was traveling inside just 3 to 5 narrow filaments in each hemisphere. Thin ribbons, covering only a small fraction of the sky, carrying the overwhelming majority of the flow. They named them atmospheric rivers, and the name was not poetry. By the numbers, that is genuinely what they are. The West Coast already had a folk name for the most famous one, the Pineapple Express, a warm plume that lines up near Hawaii and fires straight at California. When people said the rain came from Hawaii, they were right. The river begins in that warm tropical air and ends on a mountainside 2,000 miles away. And only once satellites could map water vapor directly did the ribbons leap straight out of the noise, glowing exactly where the theory had promised they would be. So we have a thin lane of sky, doing almost all of the work, which raises the obvious question: how can something so narrow carry so much? The answer is that moving water through the air is not about how wet the air is. It is about how wet times how fast, added up across the whole width of the ribbon. 2 things multiplied. First, moisture. An atmospheric river draws on warm tropical air, and warm air can hold a great deal of water. Second, wind. These ribbons ride a low, fast current of air a kilometer or two above the surface, moving hard toward the coast. A lot of water pushed fast, squeezed through a narrow gap. Multiply the moisture by the wind across the river's width, and you get the flux, the amount of water crossing the line every second. Run that calculation for a strong atmospheric river, and the number it lands on is genuinely staggering. A single one can move water vapor at more than twice the rate the Amazon pours into the sea. The Amazon, lifted into the air and steered by the wind. And it does all of this without looking like much from below. No churning rapids, no roar, just a fast, wet wind you could fly a plane straight through and never know you had crossed the largest river on Earth. And because the wind is doing the carrying, the river only rains itself out when something forces that air to rise and cool, usually a mountain range. The ribbon slams into the coast, the land tilts the moving air upward, the vapor cools as it climbs, and the water it was holding falls all at once into the same few valleys for days on end. That is why the flood lands exactly where it lands. Nudge that same ribbon 100 miles up or down the coast, hand it a different mountain to climb, and the flood moves right along with it. Now add one more piece of physics, and the story bends toward the future. The amount of water that air can hold is not fixed. It depends on temperature, and the relationship is steep. For every 1 degree Celsius the air warms, it can hold roughly 7% more water vapor. This is not a model or a projection. It is a law measured in the lab almost 2 centuries ago, the Clausius-Clapeyron relation. It is the same rule that fogs the outside of a cold glass on a warm day. Cooler air cannot keep as much water as vapor, and warmer air can keep more. 7% might sound small, but remember what an atmospheric river is. It is a machine for concentrating water vapor, so it concentrates that extra share too. Warm the planet a little, and the wettest rivers do not just get a little wetter. The strongest ones get sharply stronger because you are scaling up the exact thing they are built to gather, and the trend is already showing up in the record. As the oceans and the air above them have warmed, the most intense atmospheric rivers have been carrying more water, and the heaviest of their downpours have grown heavier. A degree of ocean warming does not arrive labeled as a degree. It arrives as a river that used to crest at the top of the levee, now cresting just over it. The lanes are the same, the plumbing is the same. What is changing is how much water each lane can deliver on the day everything lines up, which brings us straight back to the knife edge from the opening. More water in the river means a wider and wider gap between the year it saves you and the year it breaks you. Because here's the cruel symmetry of an atmospheric river. A weak one is a blessing. It drifts in, drops steady rain and mountain snow, refills the reservoirs, and quietly ends a drought that had no other way to end. Much of the American West runs on exactly this. In California, just a handful of these storms each winter deliver somewhere between 1/3 and 1/2 of the entire year's water. Think about that. Whole cities, whole farming valleys, watered for a year by a few days of the right sky. A strong one, landing in the wrong place is a catastrophe. The same family of storms is responsible for the large majority of major floods along the West Coast. Drought relief and disaster, written by the same hand, separated only by strength and aim. So the question that actually matters is not whether the rivers will come. They always come. It is which kind, how strong, and above all, exactly where each one will make landfall. And that last part is genuinely hard. A shift of barely 100 miles in where the ribbon meets the coast can be the whole difference between a reservoir filling and a town going under. Forecasters can see the river coming days out, calling its precise landing, and whether it will stall there is still right at the edge of what we can do. Scientists have even begun ranking these rivers from 1 to 5, the way we rank hurricanes, precisely because the gap between a Category 1 and a Category 5 is the gap between a welcome soaking and a calamity. Step back, and the rivers in the sky are telling you something about the whole planet. Earth does not move its water in a smooth, fair drizzle. It moves it in concentrated bursts, through a few channels, with long, quiet stretches in between. A small part of the system does most of the work, and carries most of the risk. It is efficient and it is fragile, both at once, and you find that exact shape everywhere, once you start looking. A few large storms deliver most of a desert's yearly rain. A few strong currents move most of the ocean's heat. A few faults release most of the strain stored in the ground. The world runs on its extremes far more than on its averages, and the extremes love to travel in narrow lanes. We started with a wall of gray water coming in off the sea, and a coastline bracing for it. Now you know what it really was. Not just a storm, The visible end of an invisible river. 1,000 kilometers of sky bent into a ribbon, carrying the Amazon over your head and setting it down on a single range of hills. It was overhead the whole time. Somewhere over an ocean right now. The next one is already gathering. We are only just learning how to read it.